Hi class, so thank you for tuning into this video, no? And don't forget to like and subscribe to be updated of the videos na I already uploaded. And of course, on some videos I'm going to make some announcements. Also, leave your comments below for any questions, no? And still don't forget to check your Blackboard for any other required activities, no? If any, no? So as per the academic affairs memo, no, we're going to continue with the online delivery of classes, no, until the end of this term. And like what they say, we also have to promote yung self-paced online learning and to give maximum tolerance to when it comes to giving activities, because we all know na not all students can be able to catch up to the online classes, no, kasi some might not have strong internet connection, no, and as part of it, no, I decided to make video lectures, no, instead of the what's usual, no, in order to make it more accessible tsaka flexible, no. Video lectures can be viewed, no, anytime, anywhere, no. Pwedeng balikan, no. And I divided it into topic by topic, no, to make it more manageable and somewhat medyo mabagal akong mag-upload because uh, it's much more uh, time consuming, no, and I have to exert more effort uh, compared to when we do classroom lectures, no. So kinda bear with me for the delays, no. And sa other class ko, no, I already uploaded 3 videos, no. And on this class, no, yung theory of structures 2, no, I haven't uploaded anything. So it's time na I make also video for you, no. And yung last topic na we discuss from our classroom lecture is about method of consistent deformation, no. So we're just going to continue that one. Okay? So let's start. So here are the breakdown of topics concerning method of consistent deformation. So first, to illustrate, for more clearer illustration, we first solve structures with single degree of static indeterminacy. And for single degree indeterminate structures, now we divide it into external and internally statically indeterminate. So for external, externally statically indeterminate, no, which is applicable to both beams, trusses, and frames, no, we consider either reaction forces as redundants, no, or fixed end moments or external moments as redundant, no. So next, no, using for in the case of internally statically indeterminate structures, no, we either consider internal forces or moment as redundants both for beams and frames, and internally indeterminate trusses, no. So we've already solved this one, no, externally statically indeterminate, no, reaction forces as redundant, fixed end moment as redundant, and for
internally statically indeterminate, we already solved internal moment and forces as redundant, and in the internally indeterminate process. No? So we're done with that. No? So what remains for method of consistent deformation are structures with multiple uh, degree of static indeterminacy. No? So I'm going to upload video. So for this video, we're going to solve beams with multiple degrees of static indeterminacy. And in the case of frames and trusses, I might able to upload a separate video for them, no? Although I decided na mag-focus sa frames and then just leave the trusses alone because aside sa sobrang haba mag-solve ng problems concerning trusses, no? Yung proseso niya, no, when solving for reaction are just the same as trusses with single degree of static indeterminacy, no? So for this video, no, we're going to focus on beams, no, na may multiple degree of static indeterminacy. So the concept for multiple degree indeterminate structures are just derived from the single degree indeterminate structure, no? For example, this beam, no? We have fixed support on the left and a simple support on the right, no? So we already know that this is a single degree indeterminate structure, no? So this is because this is a single degree indeterminate structure, no, we are going to consider one redundant to build your primary beam, no? So either we can either remove the support on the right, the simple support on the right, in order to make it a fixed beam, or just remove the moment on the left to turn it into a simply supported beam, no? So in this case, for the sake of the discussion, no, I'm just going to remove the support on the right. So ngayon dahil tinanggal ko na to, ito yung ginawa kong redundant, no? So ito na ang itsura ng beam niya, no? It's already a fixed support, no? So assuming na this is my original load, no? So I'm going to apply the same load on the primary beam, no? Yung tinanggalan ko ng support sa kanan, no, we know na magde-deflect siya normally. And we assume that this will become your delta 1, no? So ngayon, my next process, I'm going to remove the load and then just put a unit load, no? Dahil this is a simple support, no, it only had one reaction, no? So I'm going to put a single unit load, no, and then we'll just multiply it by b sub y later on because we are looking for b sub y. And dahil sa unit load na yon, no, it will normally deflect this way, and then the deflection is termed as the flexibility coefficient, denoted by FBB, or let's say this is just FB sub 1. No? And then the compatibility equation will be, no, your delta 1 plus delta 2, which is equal to FB1 multiplied by BY is equal to 0. No? So that is on a case of a single degree indeterminate beam. Pero what if we add another support here? Or let's say I'm just going to draw another support. No? Let's say this is your multiple degree indeterminate beam subjected to any type of load. No? Let's say this is your point A, this is your point B, and this is your point C. No? So we are going to, dahil ang degree of static indeterminacy niya is 2, no? Dito sa kaliwa, no, ang degree of static indeterminacy is 1, no? So isa lang ang tinanggal nating support. Pero dito sa bago nating example, no, we are going to remove two redundants, no? So either you remove these two supports in order to make a fixed beam, or remove the support on the middle, tapos we just remove the moment here para maging simple supported beam siya, no? So your choice, but for the sake of the discussion again, no, I'm just going to remove these two additional supports, no? So therefore your primary beam will already look like this. So 1, 2, 1, 2. This will now become your primary beam, no? And you have to take note na dahil dalawa ang tinanggal mong support, no, dalawa din yung hahanapin mong deflection, no? Let's say this will become your delta B1, and then this will become your delta C1. No? Okay, next we're going to return the reactions by applying a unit load, no, at the support where we remove the at the point where we remove the support, no? Mag-a-apply tayo ng unit load doon sa mga point na tinanggalan natin ng support, no? So in this case, ibabalik natin yung support by applying a unit load at B and C, pero 1 by 1, no? So therefore we apply unit load here, kilonewton per kilonewton, and just multiply it by B sub Y. And then we know, no, we all know that it will deflect this way, and then we're still going to solve for two deflections, no, and this, it will become your FB sub 1, no, and then this will become your FC sub 1, no. You can denote it anything you want, no. I decided na denote it this way na lang to avoid confusion, no. So yung FB sub 1 natin is the deflection at B due to 1 kilonewton unit load at B. FC sub 1 is the deflection at C due to 1 kilonewton unit load at B. Okay, next, tanggalin naman natin yung, we remove the unit load at B and then we replace it with a unit load at C, no? So 1 kilonewton per kilonewton times C sub y. And we know that it will just deflect this way again, no? This will become your fb sub 2, and then this will also become your fc sub 2. Okay, no? Therefore, no, we add, no, we add all the deflections, no? Your compatibility equation will now become, no, delta b1, no, plus, no, fb1, no, times b sub y plus fb2 cy. This will become 0. Next, compatibility equation, no, we add them to delta c1 plus fc1 by plus fc2 cy is equal to 0, no? So we just determine all the deflections here, and then two equations with two unknowns, no? That is the principle for multiple degree of static indeterminacy, no? Using method of consistent deformation, no? So let me illustrate to you by giving an example. So let's consider this example, no? So this beam is similar to what I've shown you earlier, no? So meron tayong fixed beam on the left. Let's say this is your point A, no? And we have a internal support at point C, no, which is located in the middle of the beam, and at point E on the rightmost of the beam, no? We have two concentrated loads, no, on each midspan, no, denoted as points B and D. Okay, no? So we are all aware, no, that at point A, no, we have three reactions. Let's say this is your AY, no, AX, and then your moment at A. And then we have at point C, we have your CY, we have your EY at point E. Okay, so therefore, no, we should determine the degree of static indeterminacy. No, so your I is equal to 3, no, 1, 2, and 3, no, plus 1, then plus 1, and then minus 3, no? Okay, therefore this will become 2, no? So therefore your beam is second degree indeterminate, no? Second degree indeterminate meaning we need to consider two redundants, no? So we're going to remove two redundants in order to make this a statically determinate beam, no? So we have different choices, no? We can either remove the two supports here, no, and then this will become a fixed beam, no, a cantilever beam, or we remove the support on the middle, and then the moment at A, no, this will become a simply supported beam, no, or we remove these two supports, no, remove the fixed support, then this will become a an overhanging beam, no. But in this case, for the sake of our discussion, no, I'm going to remove the supports at points C and E. Okay? So therefore, your primary beam will now become this one, subjected to original loads. No? So 120 kilonewton and then another 120 kilonewton. Okay? So this is 5 meters. No? This is 10 meters. And then this is another 5 meters. Okay? No? So, ito yung primary beam natin subjected to the original loadings, no? With removed redundants, no? Next, we're going to return, no? We're going to remove the original loads, no? We're going to remove the loadings, and then we're going to return the reactions by applying a unit load, no? In this case, we're going to apply a unit load at C, no? So this will become 1, no, multiplied by CY, no? And then we're going to apply another unit load at point E, no? So this will become now your 1 multiplied by EY. Okay? No? So we have to remember na we are going to return the redundants one by one, no? To avoid confusion, no? Okay? So no, on the first beam, no, the primary beam subjected to the original loadings, no, we know that it will normally deflect this way, no, and we're going to determine the deflections on the points na tinanggalan natin ng redundants, no. So this will become delta C1 and then this will become your delta E1. So ngayon ngayong binalik natin yung reaction at C, no, by applying a unit load 1, no, we know naman na it will deflect on this manner, no. So we're going to determine naman the deflection at point C and then the deflection at point E due to the unit load at point C, no. This will become your FC1, this will become your FE1. Okay? Next, yung due to the unit load at point E naman, it will deflect on the same manner, no? So this will become FC2 and this will become your FE2. So you have to be mindful of the sign conventions, no, para to avoid confusion, no, later on, no. So normally, no, if we remove the redundants here, no, and then just apply the loads, no, we know na your beam will go downward, no. Pero if we remove the loads and then just put the reactions, we know na it will go upward, no. So technically speaking, no, the reactions will just cancel out the deflection, no, on the points you have considered as your redundants, no. So your working equation now will be, no, just add all the deflections at point C and then add all the deflections at point E, no. So therefore this will become, your working equation now will be delta C1 plus FC1, no, multiplied by CY plus FC2, no, EY is equal to 0, and then delta E1, no, plus FE1, no, multiplied by CY plus FE2, multiplied by EY is equal to 0. No, this is your equation 1, equation 2. No, so later on, once we solve for all the deflections, no, so 1, 2, 3, 4, 5, and 6. No, we are going to we will be able to solve for CY and EY. No? Next, no? In order to solve individually for the deflections, no, we need to sketch the moment diagram of the following beams first. No? So we can either use moment diagram by parts or the conventional way of drawing the moment diagram. No? So you you will need to be practical or creative in choosing the way you're going to sketch your moment diagram, no? So kung ano yung mas madali sa inyo, kung ah kung ano yung mas madaling way to draw the moment diagram, no? Might as well do that, no? Okay, so in this case, no, I already solved for the reactions, no, in advance, no. Although I'm yet to choose kung magbabay parts tayo, because solving for the reactions will also be usable later on, no. Pero in this case, no, dahil we already have a cantilever beam, or let's say a fixed beam, no, might as well we can use moment diagram by parts, no. So we use by parts here, no, and we are going to clamp it at point A, no. So clamp it at A, no. So we have a moment due to the concentrated load at point B, no. So this is 120, no? So 120 multiplied by 5, 600, but no, this is causing downward bending, no. So this will become negative 600. Next, due to the concentrated load at point D, no, we are to compute that 120 multiplied by 15, no, negative 1,800, no. Okay, and then this will be your moment diagram, no, negative 1,800. No, we have two different moment diagrams, no, due to the 120 kilonewton at point B, due to the 120 kilonewton at point D. Okay, and we are to solve for the deflections at point C, no, which is located at the middle, no, then at point E, no. Okay, so next thing that we need to know, no, next thing that we need to know is kung ano bang method yung gagamitin natin, no, when solving for deflections. Again, I'm giving you freedom to choose whatever method you're going to use. Pero in this case, no, I can see a fixed beam, no, so might as well use area moment method, no. Bakit area moment method yung pinili ko? Because the horizontal line here, can be assumed already as your tangent from point A. And then I can be able to conclude that your delta C1, no, and delta E1 is also equal to the tangential deviation of C with respect to A, then tangential deviation of E with respect to A. And the tangential deviations are equal to the first moment of area, no, of the moment diagram from A to the point we're going to consider, no. Okay, so first let's solve for your delta C1 or your tangential deviation of C with respect to A. Delta C1 is equal to the first moment of area from A to C, no, and with respect to, no, we know that this is a trapezoid, no, so might as well determine this value, no. If this is 120, the distance between the support being considered and the concentrated load is 5 meters, no, I can say that this is also equal to negative 600. Okay, now let's determine that, no, the first moment of area due to this one is equal to negative 1/2 times 600 times this is 5 times 5 plus 2/3 of 5. And then minus, let me remind you, know that this is trapezoid, so I can either determine the centroid of the trapezoid or just separate it into a rectangle and a triangle, no. So I'm going to choose the latter, no. So this is minus 1/2 multiplied by 1800 minus 600 times 10 times 2/3 of 10, no, minus 600 times 10 times 5. Your delta C1 now will become, no, negative 1/2 times 600 times 5 times 5 plus 2/3 of 5, no. So minus 1/2 times 1800 times minus 600 times 10 times 2/3 of 10 minus 600 times 10 times 5. This delta C1 is now equal to, from the calculator, this is negative 82,000 over EI. This is expected to be negative because your tangential deviation is our tangential deviation, no, is located, no, below the tangent, no. So the tangent is above the elastic curve, no. Okay, next, to determine your delta E1 now, it's equal to, no, the area naman from the first moment of area from A to E with respect, and the centroid will be with respect to E, no. So 1/2 negative 1/2 times 600 times 5 times 15 plus 2/3 of 5 minus 1/2 times 1800 times 15 times 5 plus 2/3 of 15. no? So negative 1/2 times 600, negative 1/2 times 600 times 5 times 15 plus 2/3 of 5 minus 1/2 times 1,800 times 15 times 5 plus 2/3 of 50. No, this is delta E1 now is equal to negative 230,000 over EI. Again, negative because your tangent, no, is above the tangential deviation. Okay, no? Next beam, we're going to solve now for the deflection. We're going now to solve for the deflection at point C and E, considering the unit load at point C. No, the moment diagram using by parts will look like this one. No, so this is 10. No, this is 10 meters. No, so yan. No, and your delta, no, rather, in your FC1 is just equal to 1/2 times 10 times 10 times 2/3 of 10, and your FE1 is just equal to, no, 1/2 times 10 times 10 times 10 plus 2/3 of 10. No? Okay, let's just use this one. 1/2 times 10 times 10 times 2/3 of 10. This is equal to 1,000 over 3 EI. Okay, and then plus 10. This is equal to 2,500 over 3 EI. Next, we're going to solve naman for FC2 and FE2. The moment diagram due to the unit load at point E will look like this naman. This is 20, no, right? And this is also 20. No, so your FC1 is equal to, no, 1/2, no, rather, no, this will become 20. If this is 20, I assume this will become 10, and we can separate it into a triangle and a rectangle. No, so this will become 1/2 times 20 minus 10 times 10 times 2/3 of 10 plus 10 times 10 times 5. No, FC1 will now become, so 1/2 times 20 minus 10 times 10 times 2/3 of 10. So plus 10 times 10 times 5. This is 2,500 over 3 EI. Okay, FE, this is FC2 rather. FE2 naman will become, no, 1/2 times 20 times 20 times 2/3 of 20. Okay, no, so FE2 will become 1/2 times 20 times 20 times 2/3 of 20. So this will become 8,000 over 3ei. So we're going to combine the equations all together. So here are our working equations. Now we're going to input now all the values that we're able to solve a while ago. No, so delta C1 is equal to negative 82,500 over EI. No, delta E2 naman is equal to negative 230,000 over EI. No, so plus, no, FC1 now is equal to 1,000 over 3EI. No, multiplied by CY, no, plus your FE1 naman, no, is equal to 2,500 over 3EI multiplied by CY plus, no, 2,500 over 3EI multiplied by EY, no, then this is plus 8,000 over EI, no, multiplied by EY is equal to 0, no. So we need to be mindful of the sign convention, no, in order to not be confused, no, or just we need to be what I mean, no, we need to be vigilant about our sign convention, no. We need to be aware kung will the forces just cancel out each other at that certain point, or they will be added all together, no. So in this case, no, we already know na when the redundants are removed, no, the beam will deflect downward. So the deflections that we're able to compute are downward, so they are already negative. Pero if your deflection values are correct naman, no, no need to be scared of, kasi no matter what your sign convention you will have here, no, you will just arrive at the same answer. Pero we can just say na your assumed direction will just be incorrect, no. So I will be able to solve this using my calculator, no, the mode 5.1, no, or just review your algebra, no. Okay, no, so let's input all the values, no, but I should remind you na we're going to transfer the constant on the other side, no. So 1,000 over 3, 2,500 over 3, no, this is 82,500, no, 2,500 over 3, 8,000 over 3, no, this is over 3, and this will become 230,000. Your CY is equal to, and EY equal to, no, 145.7143, no, kilonewton, and your EY is equal to 40.7143 kilonewton. Okay, no, so we now have your we now have the reactions of your redundants, no. So going back on this figure, no? So going back on this figure, we now have your CY and your EY here, no? This is equal to your CY is equal to 145.7143, and your EY is equal to 40.714, no? So the remaining reactions that we need to solve is your AY and your moment at A, no? Okay, so uh, we can just either use the equilibrium equation, no? Summation of forces vertical, no? And then summation of moment at A. Pero I already taught you the shortcut, no, in solving for the remaining reactions, no? So ngayon you are aware na when we remove the two reactions here, no, this is how your beam will look like, no? Pero when we return, no, pag binalik ko ito, pag binalik ko yung CY, no? So this will be your reaction. This will be your reactions pag binalik ko yung CY, no? So ang gagawin ko, no, I'm just going to multiply this by CY, no? Then just multiply this by CY, no? So and then next, pagka tinanggal ko yung CY at nilagay ko yung EY, no? Ito yung magiging reactions mo, no? And we're just going to multiply this by EY, and then we're just going to multiply this by EY. Okay? So add natin, no? 240 upward, no, minus 1 times CY, no, your CY is equal to 145.7143, no, and then minus 1 times EY, minus 40.7143. Minus 40.7143, no? So your remaining reaction your reaction at point A will now become 53.5714. Now for your moment, no, 2,400 minus 10 times CY, your CY is equal to, again, 145.7143 minus 20 times 40.7143, no? So your reaction naman, your moment at A naman will become 128.571 kilonewton meter. This is in kilonewton, and then in kilonewton. So those are our final answers, no? But you may just check it out, no, while solving, no? So some possible problems that you might encounter in the future, no? This one, no? This is a beam, no? A continuous beam with two redundants, no? So you can either remove these two redundants in order to make it a simply supported beam, or remove this redundant and or one of these two to make it an overhanging beam, no? So we already know how to solve for this one. And then these are what we call the restrained beam, no? So we have two fixed supports, no? We can either remove the this support in order to make it a single fixed beam, or just remove the two moments on the left and the right in order to make it a simply supported beam, no? So o nga pala, no, before I forget, no, we since technically we don't have a horizontal reaction here due to the load being practically vertical, no, we can neglect the we can neglect uh, the horizontal reaction when computing for the uh, degree of static indeterminacy, or uh, we only have two equations that can be used: the summation of forces vertical and the summation of moment, no? Okay, no? So this is somewhat similar to the machine problem that I gave you recently, no? So in order for you to have a clue on how to solve this, no, so you can just either remove the support here and then support here to make it a fixed beam, or just remove the moment on the left, remove the moment on the right, then remove the moment in the middle to make it a simply supported beam, no? So you have lots of choices again, and it's up to you how will you be able to solve, no, for the problem, no, uh, in the future, no, kung magpa-exam man ako. And all the problems concerning the method of consistent deformation really depends, no, on how well you solve for deflections, no, which you've already encountered during your theory 1, no? So yeah.
So that ends our discussion for this video. No, on the next video, either we're going to continue discussing on method of consistent deformations for multiple degree indeterminate frames, no? Kasi beams na tayo dito, or we move on to three moment equations, no? So I'm going to choose either of the two, no? Pwede kong i-skip yung MCD for frames and mag-move na tayo into three moment equations, no? Depending on the situation, no? So just watch out, no? And see you, no, on our next video.